So I am Mickey. That's Jesse. That's our Twitter handles. If you want to ask us questions about anything we give at this talk, please feel free to reach out and ask us, even next week or whatever. We're happy to help. About the agenda of this talk, well, we're going to start with a little bit of high-level introduction into what is a driver in Windows. We can keep it high level, and then we're going to go get more and more technical as we go along. Part of the things we're going to discuss is what the problem is, give you some funny examples of it, the tools that you need to exploit for yourselves, and a couple of funny stories about disclosures. This topic is not new, so bad drivers have been known to be found in the past decade. They pop up, one here, one there, 3 here, and you get a little blog post and description and excuse me, how to use them, and it just goes away after a while. The vendor patches it and fixes it or not, and it stays there and then just continues on. So here are some of the examples we used in our talk and based our some of our code on, so we thought it would be best to give credit. More information can be found in these links. We'll have the slides available on the GitHub soon after the talk or early next week, and we'll explain for that later. Let's start with the biggest, the smallest, the simplest explanation. I'm sorry, English is not my first language. Why are we talking about Windows and not Linux or Apple? Linux drivers are basically all in the tree. So except for specific examples that are proprietary code, most of the Linux drivers are available in GitHub or open source, and you can find them and look at them. Apple is a closed garden, so whatever Apple does, Apple knows and Apple sees, so we don't really care. There is a caveat. Apple does have their Windows drivers for their hardware. We did skim those, but we didn't find anything substantial there. What is a driver and how it's used? So basically in the computer and operating system, you have a user space, you have kernel space, and then you have the hardware. For applications in user space to talk to the hardware, you're going to need some sort of way to do this securely. Otherwise, you violate every known concept of a security boundary ever. Right? You don't want a Ring 3 or user space application to be able to read and write SPI flash. It's just wrong. So we have this concept called drivers. These drivers are running within kernel space. They communicate with the kernel. The kernel gets requests from the application, passes it on to the driver. The driver does its magic, communicates with the hardware, and goes back and forth. It's pretty straightforward. These drivers in Windows are signed. Now, for a driver to run and be executing in kernel space in these days, it needs to be signed and it needs to be certified by Microsoft. We're not going to go into the entire process of how drivers are certified by Windows. It's not easy to explain. There's a back and forth. I know some of you are smirking right now. Yeah, because you probably tried to sign drivers with Windows. There is a reason for that process, but it's not quite straightforward to get out from reading blog posts on the internet. The key point in this slide is Windows 10 signing process, right? So Microsoft introduced this new process called EV. EV stands for extended validation. If you want an EV signer certificate driver, you need to have this EV certificate, which allows basically Microsoft to co-sign the driver with you and give that WHQL certification side by side, so you have a driver that's certified by Microsoft and operates and everything's great. EV, these are the slides we found from a Microsoft presentation given in Shanghai 2015 when they introduced this. Funny thing about this is that the bad guys reference here, and that EV certificates are better because it means less malware, but not for legacy. So if you have an old driver that's already signed, do whatever you want with it. However, Microsoft is a good guy that will let you load the driver even if the certificate's expired. We do have one of these drivers that for some reason loaded, and we kept double checking the properties, and it's just expired, the certificate. What the hell's going on? So we ran Sign Tool. Sign Tool said it's not within the required period of verifying. No idea why it loaded. It's still loaded. I don't complain. So at this point we were like, maybe we'll get our own EV certificate. We'll try to make our own example driver and, you know, have some fun with it. We saw this list of things to do, of getting it, and you know, you have to have the legal agreements to sign on behalf of your organization. I don't think so. It's just too much of a hassle. We work for a company. That company has their own driver they develop. They signed it with Microsoft. I don't want to risk anything potentially with Microsoft, so highest of notes.
So let's take a look at some of the issues that we've seen in the past with signed drivers. And one example that that a lot of people know about is read-write everything. And there's also LoJax is one of the more interesting malware that we saw that was using signed drivers. Slingshot was another APT that was using this class of driver specifically to bypass Windows protections. We've also seen this type of driver being used by game cheating engines or anti-cheat software. There was an interesting case, Capcom driver, where this driver was signed by Capcom for a video game that it would turn off SMEP protection, execute code that you pass in from user space, and then continue on. And that was found pretty quickly, and people were able to know to block that. But these issues keep popping up individually, so we wanted to look across the spectrum a little bit more. There's some nice examples, write-ups of there's a vulnerability in a MSI driver, and here's how to use it to escalate from user space non-elevated to entity authority system by using one of these signed drivers. So to take a little bit of a closer look, read-write everything, it was designed to give you the ability to look at these hardware interfaces in your system, basically explore the system, see what the state of the machine is. And it basically has a user space app and then a signed driver, which is intended for this purpose. But the problem is that it allows access to components that have really important security properties, and they need confidentiality in some of these resources and integrity in other resources. So you're basically given free rein to arbitrarily read, write, modify some of the interfaces that Windows depends on. Windows security depends on these not being tampered with. So this was an interesting app. But then LoJax was a malware that was found in the wild. It was an APT that they actually brought a copy of that ring write anywhere driver along with them as part of their infection. Their implant tool used read write everything in order to gain direct access to the SPI controller, and then they were able to use that in order to write their own malicious module into the system flash and persist in that UEFI firmware that would survive reboots, operating system reinstalls, because they have the ability to directly talk to the hardware through this mechanism. And even if your system did not have this read-write everything driver on it, they just brought it with them, they were able to load it and use that capability in a really interesting attack. There was another APT campaign that also brought their own driver. Their driver was not signed, but they exploited 4 different drivers that had read-write MSR capability in order to get arbitrary code execution in the kernel and bypass driver signing enforcement, so they could install their own kernel rootkit. So this is out there actually being used in the wild by real attackers. So there's a few different reasons why you might want to use one of these drivers. Basic one is just privilege escalation from user space. Either escalate a user from a normal unelevated user to admin user. There's also just getting code execution running within the kernel itself. Another possibility is you can use some of these drivers to disable, bypass Windows security mechanisms, and sometimes that can be used in order to escalate privilege within the kernel or just get access to resources that you shouldn't get access to. There's another motivation where essentially getting access to the hardware itself is really useful. You can modify system firmware, you can modify device firmware. There are a lot of devices that still have unsigned firmware, and you can go basically write your malicious modification to either the system firmware, get code execution before the operating system loads, or modify a device and have a persistent implant in a particular device. And there's some other things you can do with direct hardware access, but those are some key ones that we wanted to specifically call out. So there's a few different attack scenarios. If the driver is already on the system and loaded, the driver itself controls the policy for who can talk to this device. So many drivers, you don't have to be admin. You can be a normal, non-elevated user in order to talk to this particular device. There's another scenario where the driver is on the system, but it's not loaded yet. And in that case, you do need admin privileges to load the driver. We have found signed applications that you can use to load drivers that are signed by well-known trusted vendors that you could potentially use one of these applications. There'd be a little UAC pop-up that says, would you like some trusted vendor to modify your computer? And that might be a means to load the driver if you don't have admin privileges. But you can also just wait. So if it's already loaded, you don't need to be admin. If it's not yet loaded, you do need admin, essentially. And there's also the scenario where the driver isn't on the system, all of your drivers are fully up to date. Malware can bring a driver with it and load that. In this case, you do need to have escalated to an admin in order to load the driver, but there have been a lot of privilege escalations. You can bring an older version of the driver, so even if the newest version has been fixed, in many cases the old vulnerable driver will still be loaded into Windows or loadable into Windows, and you can just bring the old version, load that, and use this kind of capability. And LoJax did this further in the Wild APT campaign, where they brought an older driver, they were able to load it and get direct access to the hardware and implant the UEFI firmware. So we've seen this pop up every now and then, just one at a time. There isn't really a industry-wide fix for this problem or an industry-wide effort to go fix this. So we wanted to take a look and see how hard it is to find these drivers and how widespread it is. So we focused on, because we're interested in signed drivers so that we're loaded into Windows, we threw out any that we found that weren't signed. Because we're looking for drivers that talk to hardware interfaces or have that kind of capability, we looked for drivers specifically from firmware and hardware vendors. And then just to make it a little easier, we went with the smaller drivers that would probably be more simple. So also looking for things like read-write MSR opcode, move to control register, in and out opcodes. Those are specific x86 instructions that are talking to drivers or talking to devices or hardware in a way that we're interested in. One other thing to keep in mind is that there's two different driver, there's two different mechanisms or frameworks that you could write your driver. There's the older Windows driver model and the newer Windows driver framework. With the older version, your driver would just call IO create device and then write a address of a handler for all of the requests that user space is going to make to your driver to a specific address within a structure that it passes to this IO create device function. The Windows driver framework has changed a little bit, but it's a similar kind of concept where you have a couple functions that are set up, and eventually you do have a main dispatch or ioctl handling function that will handle all of the requests from user space. And I don't know if we mentioned it, but ioctl is basically IO control. So there's a specific number that you can say, I want ioctl 1234, and the dispatch will call your kernel handler and say, here's your IO request packet with request 1234 and the data that was passed from user space. So there is a little bit of a difference where in IO create device versus this create device secure function, if the driver is calling a create device secure, it can actually specify a security descriptor, which is a policy that says who can talk to this driver and what type of access they have. This is an example of one of these SDDL strings. In this case, it's a discretionary access control list that allows generic all to local system and generic all to built-in administrators. Most of the drivers that we looked at don't bother to set any kind of policy, so a normal non-elevated user can talk to these drivers. So we essentially spent 2 weeks looking for drivers. We skimmed through hundreds of driver files, just doing manual disassembly analysis, looking for this type of behavior. We found 42 different vulnerable signed drivers. We found 42 vulnerable signed x86-64 drivers. We did find a lot that had a 32-bit version, so it was around 80-something total files. But we did find one Itanium driver that I don't know if anybody still has an Itanium machine out there, but we've also found more drivers since, but there were 42 drivers, 42 x86-64 drivers that we were looking at. But the types of things that we found were things like, basically you could ask from user space for the kernel to go read and write virtual memory in the kernel, or do read and write to physical memory addresses. You could go talk to MIO devices, model-specific register, arbitrary read-write, control register access, talking to PCI devices, some SM bus access, just basic in and out. So here's an example of a mem copy that we found in the kernel where they literally are taking the source, destination, and size for this copy operation from user space. There's no checks of any pointers, no pointer checks, no length checks. You can literally just ask the driver to go copy memory around for you. This can be used to modify kernel code and data structures. PatchGuard will detect some modifications. It doesn't detect them all, though. So if you have a primitive that's this flexible, you can do a lot of interesting things with it. You can copy from user space into kernel memory the other way around. It's really useful. Another thing that we found is just basic arbitrary physical memory read and write. In this, it's intended so that you can use it to go talk to device drivers and do MMIO access. In this case, there's also no sanity checks. You could basically have any address, any size, and go try to call this function mmap IO space. There has been a change in how Windows deals with this function as of 1803, where they've tried to limit the scope of what you can do with this physical memory write only to those MMIO addresses. So older systems before 1803, you could just map any kernel address and do a read and write there also. But even after 1803, you can still go get direct access to the hardware and do some pretty interesting things there. There's also drivers that just expose the physical to virtual mapping, so you can look up addresses in virtual space and find their corresponding page in the physical address layout, which is it's useful for dealing with iactls that give that kind of physical address, but it's also useful for things like rowhammer, where it's like knowing where things are mapped physically into the address space. This type of functionality can be really useful. So another thing that we looked at was just arbitrary model-specific register read and write. Here's an example where they're taking the address of the model-specific register to read, no filtering, directly give you the data back. So if you're not familiar with model-specific registers, these are internal registers within the CPU that, like, you have your general purpose registers for normal executing code, but these special purpose model-specific registers are in addition to that. And they were originally used for experimental features that Intel wanted to try out, and some of those experimental features, they decided these are really useful, so we're going to turn them into architectural model-specific registers, or MSRs, such that from a certain point going forward, they're committing to support this particular usage model for the value that you put into the MSR will be used in a architecturally defined way. And they do have special opcodes, special x86 opcodes, read MSR and write MSR, in order to access these registers. One interesting point is that you can only access them from ring 0. So ring 3, if you try to read an MSR, you'll get a fault, and it won't allow you to get that data. But we have a primitive here where you can read MSRs, and there's some pretty useful things that you can get just by reading the MSR. We also found model-specific write primitives, and there are some really, really critical model-specific registers that are especially interesting, like star, C star, L star, and C star, where in order to even transition from user space into kernel space, or ring 3 into ring 0, when you execute a syscall instruction, it will, as part of that transition going from ring 3 into ring 0, it will take the address that's stored in this L star register and use that as the address that it starts executing in ring 0. So if you have the ability to write to this register from user space, that's pretty dangerous. So there's also control registers, and there's a lot less control registers, but they store some key control bits for the processor. CR3 is the base of the virtual memory paging tables, so knowing where that is could potentially be useful. CR4 has some other security controls. CR0 has some security controls. So in this case, we have an arbitrary ability to read any of these control registers, including the base of the page table structure in kernel space, not the user space copy of the page tables. And there's also control register write functions, where you could take an arbitrary value, an arbitrary control register that's taken directly from your user space input buffer, and write the value to the control register. And some pretty key ones that some of the security controls in Windows depend on is supervisor mode execution protection. That basically is one of the features that helps protect against a number of different attacks that have been very successful against Windows in the past. There's also this write protect bit in CR0, where if the write protect bit is not set in CR0 and the kernel or ring 0 code tries to write to a page that is marked as read only, it will completely ignore the permissions in the page table and let you do the write anyway. So it's an interesting control. So it's kind of security hardening, but it's useful to know about. If we can write to that, that can help us. Other things are just arbitrary I/O port write. You can write arbitrary values to arbitrary I/O ports. It's what you can do with that is platform dependent. You could possibly use that to modify system and device firmware. We saw a really cool vulnerability last year involving a ASpeed BMC configuration where there were debug features that were accessible from the host, and you could, through I/O reads and writes, arbitrarily read and write into the BMC address space. Laptops likely have an embedded controller that you can talk to over I/O access. And then there's also legacy PCI access over I/O port CF8, CFC. There's also just functions to literally do that legacy PCI write. So there have been issues with security of PCI devices, and that comes up a lot. So to kind of look at the MSR case a little bit more, essentially the LStar MSR is pointing to an address into kernel memory where we don't know exactly where the kernel has been loaded. There's address randomizations happening. So when this transition happens, when you go from user space to kernel space, it starts executing at the address that LStar points to. So if you can write to LStar, we can basically allocate a buffer in user memory, and then when that transition happens, the very next syscall that happens, it'll start executing from your pointer instead, but there's some complications to that. So one of the features that I mentioned, supervisor mode execution prevention, is intended to stop this feature. There have been a lot of bugs where you could get the kernel to jump to your pointer, and they added this feature to the CPU, I think in Sandy Bridge, where maybe Ivy Bridge, but it's essentially a feature where if the CPU is executing in a ring 0 and it does a code fetch to a page that's in a user mapping, it'll cause a fault. And this is controlled by a bit in the CR4 register. So if we have a read-write primitive for control registers, we can just read this bit or we can read the CR4 value, clear the bit, and write it back to CR4 in order to get around supervisor mode execution prevention. There's another complication that there needs to be a little bit of state change when you're transitioning into the kernel space. So although it starts executing in ring 0, it hasn't fully switched into kernel space. So you need to do a little bit of extra work entering and exiting your payload there. And then there's also kernel page table isolation. So as part of the meltdown mitigation for one of the Intel CPU issues, they basically isolated the kernel pages so they have two different sets of pages, one for user space and one for kernel space. So we do need to know the address for those kernel page tables in order to fully be able to switch into kernel space. But if we have an ioctl that we can arbitrarily read CR3, then we can get the address of that kernel page table base, so that when we build our payload, we could just swap in the kernel page table pointer and do what we want to do. So we have a couple little demos of switching of some of these features.
Quick note, all these demos are in PowerShell.
So we have a basic so this one is not PowerShell, but this is just a simple. Yeah. So in order to do our research, we basically made a simple tool to load any arbitrary driver for us. So instead of needing to write a helper to load it and deal with it, it's just a simple tool to load a driver, create the service, start the service for us so we could try things out. So in order to do this, we were running as administrator. The other demo that I'm about to show is not running as administrator.
Let's go back.
Yeah. So in this case, we basically are reading some state from basically the kernel is being loaded at a random address. So from user space, not elevated at all, we can read the address of that entry point into the kernel and understand where the kernel is loaded. So this can help us with further attacks that depend on where the kernel is loaded into the address space. We also know the base of the page tables is this second value. So when we're building a payload, we can use this value to make that easier. Yeah. So there's also the SMEP bit in CR4 where we can also, like in this case, we read CR4, we saw that it was enabled, we cleared the value, we wrote it back, we see that it's still it's disabled now, and there is a feature in Windows called Patch Guard that will go and look for configuration of the system, look for dangerous things, and we found a write-up that said that they were able to measure that they were reading these MSRs every 30 minutes. So that's a lot of time to get your malicious code to run. And so we were testing. It didn't crash even after like 45 seconds. We did see some cases where it would crash after you wrote to the MSR, but it seems like plenty of time in order to get your payload working if you want to use this for...
I don't know if you can calculate it from uptime.
What was that?
It was 1903.
Oh, yeah. And this is on a 1903 system, so it's has the latest version of Patch Guard. Okay. So some of the problems is like we took all of these drivers, we uploaded them to VirusTotal. None of the drivers came back as malicious. They're loaded by Windows, but AV isn't really helping us with this issue because you can use a lot of these drivers to attack AV and bypass some of those protections. So we were hoping that we could actually fix this. So Microsoft does have a virtualization-based security and hypervisor enforced code integrity. Those are only present from 7th generation CPU and newer. Also, there are compatibility issues that prevent you from turning this on, and HVCI will help against some of these issues, but not all. And I have a Kaby Lake laptop that is pretty new and should support it, but I have compatibility issues and I haven't been able to actually turn on this feature. There's also some enterprise device guard policy that you can configure to block known drivers once they're known to be vulnerable, but there hasn't been any really industry-wide fix for this yet. So we're hoping to fix that. So all of these drivers that we found originally were just through manual analysis. So we were looking, how can we actually automate this? And started looking at the Anger framework for symbolic execution. And if you're not familiar with Anger or symbolic execution, it essentially allows you to dynamically execute the parts of a program, and every time you get to a conditional branch, it will try to execute both paths and see what happens. So it's really useful, but it's easy to run into issues. So I got an initial script just to try out the idea working in about a day, and it works really well in some cases. In other cases, the code is complex enough that you run out of memory and you have a state explosion because there are so many conditional branches that it had issues. But for what that actually looked like for trying it out, we had a specific driver that we know is vulnerable, and we know the address of the handler that does that main IACTL dispatch, is at a particular address, and we know the address of a write MSR opcode that we want to search for and see if this is actually taking data that's passed from user space. So essentially, you just need to load the driver into Anger. In this case, we don't care about libraries, so we'll not load libraries, and then create an Anger execution state object that starts execution at the IOCTL handler, the dispatch function. And we can take that IO request packet, that structure, and basically create symbolic regions for those parts and set pointers so that when we're starting execution at the IOCTL handler, it will have these symbolic regions as the input data that we're passing into this function. Then you can create a simulation manager and just let it start executing code from the IOCTL entry point with a target address of the write MSR address. So we're trying to reach that address. If it's found, we just print that we print that a path was found, and whether the input data to this write MSR is taken from the input buffer if it's symbolic data. And it worked. It completed in less than 5 seconds, and we proved that when we reach this write MSR opcode, that the address and data that will be written to the CPU register is included in the input buffer. It even tells you the specific DWORD offset into the input buffer for where you need to structure your data to talk to this driver. And it completed in 5 seconds. Literally, the last 3 slides that I showed you, that's the entire script to do this and prove that this is actually taking input from the user. Another issue is that we want to automatically find that IOCTL handler ourselves, so we don't have to manually open every driver, do some disassembly, find that initial dispatch function. So for a WDM Windows driver model drivers, it's a lot easier. We can easily just set a memory write breakpoint on that structure element in the driver object. And this script right here, that's all you need to find the IOCTL handler for these WDM drivers. We can also automatically find the IOCTL number. So you have a driver, there's a write MSR. It'll tell you that there's a write to a control register or an MSR. It'll tell you the number you need to pass for the IOCTL. It can tell you what values you also need to put into the input buffer. So in this case, this list of constraints down at the bottom were automatically detected, and Anger can actually simplify those for you. So these 3 constraints at the bottom basically are simplified to the value at the first DWORD in the input buffer needs to be 4, and then the second, the third and fourth DWORDs are the value that's written to this CR4 register. So we can actually find a lot of information automatically. There are some problems with this. Anger is based on VEX, which was part of Valgrind, so it was all user space applications. And as far as we can tell, it was never used to analyze privilege code because it literally has decode errors when it runs into some of these privilege opcodes. So the decompiler and instruction lifter, it lifts into an intermediate representation, and that part of the code, it runs into decode error and it doesn't know what to do. So there is some functionality that was added in the Python framework on top of that, where you can write a Python module to kind of emulate or implement what this opcode should have done. So we were able to take advantage of that and have it work more reliably on more drivers. So one other problem is that it currently only supports, at least the tool that we wrote, only supports WDM drivers. We do detect if it's a WDF driver and have some ideas on how to make it work with WDF drivers also. It's just a little bit more indirection and hooking, but it should be fairly straightforward. And then there's the issue that some drivers are a little bit more complex and cause it to run out of memory. I've had it run out of 64 gigs of RAM, so we need to fix a few things. So I'll let Mickey take it.
So now for a little bit of naming, shaming, and faming. We talked about 20 total vendors. These are the ones that we can disclose right now. Some are not ready to release updates. Some did not respond. Some said acknowledged, but we haven't heard back from. And some are really working on a fix, but because they're in regulated environments, they require more time to go through certification. So we're not going to disclose them. We're going to go through everything we've been through, talking to these guys and these companies since late April, early May. We're going to start from the best example to the worst. The best example we had is with Phoenix. Phoenix is one of the big 3 IBVs. I have never heard or experienced a better response than Phoenix. We started with the first disclosure batch to send out to vendors, I think Monday that week. And we said, yeah, we'll finish it up. We'll send it on Tuesday. Obviously, it ended up Friday, 5 p.m. And we sent out the emails and we went home. Saturday morning, we got an email back saying we acknowledge the issue. We're working on a fix. Within 6 weeks, they already had a fix ready to deploy to customers. This is textbook. Like, I've never ever experienced anything like this, especially with a driver. We also sent an email to CERT and CERT-CC. For some reason, it got lost in communication with US CERT. I did end up calling them a couple of days ago, and they did receive it. So I don't know what's going on from that perspective. We did get a receipt, but no actions were prescribed for us from CERTs. Microsoft. Now that's a story. So Microsoft's model of the operating system is basically give third parties the option to write their driver, right? It's like, I have a company, I have a product. Here, write code to interface with my product. The problem with this class of issues is a lot of drivers fall into that caveat where someone might write bad code. So what can Microsoft do about it? They can't just say, hey, okay, people, write some code, but don't make it bad. It's a bit problematic. So we had an initial discussion with them and send them a note, say, hey, what's your view about this? And we got a response from MSRC Tier 1 that said, not a problem, talk to you later. We sent another email later on asking if they're really sure. It was a back and forth. And at the end of the day, after quite a few rants on Twitter, we ended up getting to communicate and ended up doing a couple of face-to-faces here in Vegas. It changed the entire conversation. I'd like to say thank you to Krista Anderson and Nate Warfield for being very good at communicating and forthcoming and trying to help. Also to Kimberly, Marissa, Mary, Eustace, and Gaurav, I hope I'm not butchering that name, for helping from MSRC side to clear everything up and help sort things out. Now, the worst driver award goes to ASRock because this is one of 4, I think, one of 4 signed drivers that does all of this. So it's quite impressive. The You Tried award goes to NVIDIA for telling us that the driver that we found is internal, so it doesn't merit a CVE because it requires a security hardening effort internally, although it is distributed by MSI on their website as a tool for updates for their graphics cards. So it's internal tool, but it's distributed by an OEM on the internet. Okay. The worst ones are these 4 that did not respond. So out of these 4, there is one that completely doesn't respond. So at least some of them sometimes respond. But Realtek, I've had researchers during this time in Vegas. We talk to each other and we share notes and we discuss experiences like, oh, this vendor sucks, this vendor's great. And no one in Realtek is answering any emails. So if anyone from Realtek sees this, please check your inbox and reply to something. A few advisories are coming out. So Phoenix did June 21st within amazingly quickly time, already sent to OEMs. So the fixes that Phoenix, Inside, and AMI will release, the 3 big BIOS vendors, are going to go get distributed to OEMs, and OEMs will then distribute it to customers. Intel had a fix on July 9th, Huawei in July 10th. Let's see, Inside is today, it's the next slide, and a couple more coming out next week. We can't talk about it, and a few more until the end of the year. Inside was kind enough to send us this statement. I'm not going to go through it, but the gist is they're fixing it. Microsoft sent us this statement. I'm not going to go through this because we've been through enough. And now I'm moving to conclusions. So basically, bad drivers are bad. People that write ring 0 code and write it badly are a danger to society. Some of these drivers, like the easiest way to fix this is, okay, I'm a vendor, I wrote a driver, I own up to it, I revoke the certificate, done. Can't load it anymore in Windows 10 at least. So getting vendors to revoke the certificates is not as easy as sometimes, like we had with Phoenix, but it will be a great help to do this. Like the biggest majority of the majority of drivers that we've seen are old. They're not new, brand new, 2018, 2017. Some of these go back to 2008. So just revoke the certificates. This is like a big problem. It's not just specifically, it's just a class. Again, multiple researchers have disclosed these drivers separately at a time, but the problem is systemic, and we're hoping that at some point this can be fixed in a larger scale. Windows 10 is moving towards this. There's mitigations in place. There's HVCI, virtual-based security, but you have to have a 7th gen CPU and above for HVCI to work, and even then, not always does it work. We are going to release all our code, C#, C++, and PowerShell examples on GitHub with the latest slides and the videos, and our tracking for all the drivers and where you can find them. Please check this GitHub on August 13th. We did have this internal debate of whether to release it today or in 3 days, but because it was so close, we just decided to sort everything out, get through Vegas, and upload it on the 13th. And I think we're done.